Hello, in this podcast we're going to learn how to use special physics terms to describe motion. First we're going to learn about vector quantities and scalar quantities. Then we're going to learn how to describe the location of an object by its position, displacement, and distance. And finally we're going to look at elapsed time, speed, and acceleration. Let's get started. Let's take a look at quantity, but first let me just describe this format. This is known as a Freyer diagram, and it gives us four different ways to explore the meaning of a term. The formal definition, characteristics, examples, and non-examples. So let's take a look at what a quantity is. So it's a numerical description of something that is either measured directly or calculated from direct measurements. Some of its characteristics are it's numerical, it's measured or calculated. We also know quantity as variable, and we, especially in math, use the term variable probably more than quantity. But in physics, we're going to use the term quantity more than variable. Some examples. The car's speed is 44 miles per hour. Notice it's numerical. The woman's height is 6 feet 4 inches. Some non-examples. The car's speed was faster than the mopeds. This is a comparative description, not a numerical description. The woman was tall. That's a qualitative description, not a numerical description. Let's look at a scalar quantity. It's a numerical quantity that has only magnitude. Its characteristics has a numerical magnitude. It's measured or calculated, and we also will know this as a variable. Examples, we have temperature and we have weight. For instance, the temperature is either negative 30 degrees Celsius, very cold, or positive 85 degrees Celsius, very hot. But there is no direction to the temperature. The temperature may be increasing or decreasing, but it's not like it's 85 degrees Celsius in the south direction. That doesn't make any sense. Same thing with weight. This person looks like they're coming in at about 188 pounds. Again, there's no direction to that. It's not 188 pounds upward or rightward. So these things that are represented only by a number, only by a magnitude, are called scalar quantities. Now let's look at some non-examples. Here we have force and velocity. Force is not a scalar quantity. It has a magnitude, 300 newtons, but it's 300 newtons pushing to the right. And here in the example of velocity, it has a magnitude, 25 meters per second, but it also has a direction. The car is moving to the right, which we call the positive direction. Let's look at the opposite of a scalar quantity, which is a vector quantity. It's a numerical quantity again, but it now has both magnitude and direction. So its characteristics, a numerical magnitude, it has a numerical angle or a plus minus direction on the x or y axes. It's measured or calculated, and again, we often refer to this as a variable, especially in math class. Some examples. We have velocity and force. Here, the velocity is negative 25 meters per second. The negative sign means that it's moving to the left, and the 25 is the magnitude. So I just want to make a comment here that's true in physics. When you see plus and minus signs, they have nothing to do with the value or magnitude. They have everything to do with the direction. And here's a force. So the person holding the leash is pulling up on the leash at a 40-degree angle. So this is an example where we use a plus or minus sign to show the direction, and here's a case where we use a directional angle to show the direction. Let's look at some non-examples. Temperature and weight, and of course we described in the previous slide how it makes no sense for them to have direction. Okay, now that we had that background information, let's move on and look at some specific quantities we use to describe motion. And position is the first one. It's the location of an object based on an origin or reference point. It is a direct measurement. It's a vector quantity. It has both magnitude and direction. Positive is upward or rightward of the origin. The symbol we use for position is lowercase x, And the SI units, the System International units, are meters, which we abbreviate with lowercase m. Some examples of position: the sprinter's positions at the starting line is x equals 0 meters. That means that they're right on the origin. Kind of makes sense in a 100-meter race that we'd make the starting line the origin, but you don't have to. The finish line could be the origin. In this example, Usain Bolt's position at the finish line is 100 meters. So again, if the starting line is the origin, then the finish line in a 100-meter race is going to be 100 meters rightward of the starting position. And let's look at some non-examples. The entire trip had a position of 20 kilometers. This describes a change in position. The 20 kilometers is a change in position, not a specific position. And the orchestra pit's location is below the stage. This is the description of a location, but it's a qualitative description, not quantitative. Moving on, let's look at displacement, and that's an object's change in position. Its final position minus its initial position. Mathematically, we would show that as delta x is equal to x sub f minus x sub I. Now let's break this down. Whenever you see delta, this triangle is the Greek letter delta, happens to be the capital delta, and it means a change in whatever variable or quantity is listed next. So this is change in position, and that's what displacement is. And the subscript here refers to the final position, and this subscript I refers to the initial position. Characteristics: this is calculated. We can't measure the change in position directly. We have to measure the final position and the initial position and then do the subtraction. That's why we call this a calculated measurement. It's a vector quantity, has both magnitude and direction. Once again, positive is moving upward or rightward. The symbol is delta x, and the SI units are meters. Some examples. Here, the boy walked from D to A. His displacement was -5 meters. So the boy started here at D and walked to A. This diagram is showing that the distance between D and A is 5 meters. He was walking leftward, so his displacement was negative, meaning leftward, 5 meters. Here's another example. The boy walked from A to B to C to D to A. His displacement was 0 meters. Now you may say, wait a minute, he traveled a distance, and that's true, but displacement, let's look at the definition, it's a change in an object's position. So he started here and he ended here. His position didn't change from the initial position to the final position. Let's look at a non-example. The boy's displacement from A to B to C was 8 meters. And that's not true. He walked a total of 8 meters, but his change in position from A to C was only 5.8 meters. And if you're wondering where I got that, I'm just making a right triangle here out of A, B, B, C, and AC. And so using the Pythagorean theorem, I came up with the change in position as 5.8 meters. Here in a second non-example, the rock displaced 5 liters of water. This is an accurate use of the term displaced, but it's a different meaning of displacement than what we mean in mechanics. Let's take a look at distance. It's the length of the path an object travels. So this is a little different than displacement. Characteristics, once again, it's a calculated measurement. It's a scalar quantity. It only has magnitude. It's also sometimes called path length. Its symbol is lowercase d, and the SI units are meters. An example, the boy walked a distance of 3 meters from point A to point B. The boy walked a distance of 16 meters from A to B, B to C, C to D, and D to A. Looking at non-examples, the boy walked a distance of -5 meters from D to A. So from D to A, he did walk 5 meters, But distance is a scalar quantity. It only has magnitude. So we do not use directional signs to show that he was actually going leftward. His displacement would be -5 meters, but his distance was 5 meters. And lastly, the cyclist traveled a distance of 120 miles. So right here we can see the distance between his house and the factory was 120 miles. We might say that's 120 miles as the crow flies, but it's a straight line. So his change in position or displacement was 120 miles, but we can see here he had to travel on an S-shaped road, and that, of course, is going to be longer than 120 miles. Elapsed time, the time between two events. It's the final time minus the initial time, and here again we see this delta function. Delta t means the change in time, specifically the final time minus the initial time, and it's important that you do the subtraction in that order, final minus initial. Characteristics, it's a calculated measurement. We can measure time directly, but we cannot measure elapsed time directly. It's a scalar quantity. It has magnitude only. Its symbol is delta t. SI units are seconds. Examples. The seminar lasted 6 hours because it started at 11 and ended at 5 p.m. The movie was 2.5 hours long. Non-examples. The elapsed time is 5:33 a.m. This is a specific time or clock time, not the time between two events. The 400-meter race has a longer elapsed time than the 100-meter race. Again, that's comparative, not numerical. Let's look at speed. The definition is the distance an object travels per unit of elapsed time. Mathematically, we find the speed by taking the distance the object travels and dividing it by how much time it took to travel that distance. Some characteristics are it's a calculated measurement. Notice we had to do this division calculation to come up with the speed. It's a scalar quantity. It has magnitude, in other words, numbers only. It doesn't have a direction. The SI unit is meters per second. Let's look at some examples. We have the skydiver, and the skydiver's terminal speed is 55 meters per second. That's about 120 miles per hour. And we look at the speedometer on the car, and we say the car's speed is 58 miles per hour. Those are examples of speed. Let's look at some non-examples. Once again, with the skydiver, if we say the skydiver's terminal speed is downward 55 meters per second, that's not a good use of speed because notice it has a direction with it, downward. If it's speed, we're only interested in the number. Let's take a look at acceleration. The definition is the rate at which an object's velocity changes. Some characteristics are, first of all, it's a calculated measurement. It's a vector quantity as magnitude, in other words, as numbers, and direction. It represents an object speeding up or slowing down because that's a change in the object's velocity. The symbol is lowercase a, and the SI unit is meters per second, which is also known as meters per second squared. Some examples: the bicyclist sped up from 5 meters per second to 10 meters per second in 10 seconds. And the car slowed down from 20 meters per second to a stop in 5 seconds. And let's look at two non-examples. The girl was walking at a speed of 1.5 meters per second, and the car was parked in the driveway. These are not examples of acceleration because the girl's and the car's speed are not changing. Well, this wraps up what we wanted to learn about describing motion with words. Let's take a look at our key terms. Quantities are numerical descriptions. Scalar quantities have magnitude only, in other words, only numbers. Vector quantities have both magnitude, that's a number, and they have a direction. Position, displacement, and distance are used to describe the physical location and changes in the object's physical location. Speed describes the rate at which an object's distance changes, in other words, how fast or slow it's going. And we can calculate the speed by taking the distance the object traveled and dividing it by the amount of time, the elapsed time, that it took to travel that distance. And finally, acceleration is used to describe the rate at which an object is speeding up or slowing down. Well, I hope you found this information helpful, and have a good day.